In brown bag session. So today I want to continue discussion that we started having the last time on Legion's physical analysis. So just to refresh everyone's memory of where we we're talking about the physical analysis stage of the Legion pipeline. And we were looking, previously at, how these physical analyses actually, operate in terms of how they traverse equivalent sets to look for what copies they have to issue to update to maintain the coherence of data, for distributed memory and multiple GPUs and stuff like that, right? So each of these physical analyses traverse these equivalent sets, right? They do some analysis, which we looked into in great detail to figure out, what copies and reductions and fills and other stuff have to be issued. And we saw that those copies and fills and stuff were being recorded, in these copy-fill aggregators, right? And today, the main topic that I want to talk about today are these copy-fill aggregators and how they work, and what they do and what their purpose is, and some of the tricky cases that can occur when you're actually implementing these copy-fill aggregators inside of Legion. One thing I do want to refresh everyone's memory about is that effectively the reason to have these copy-fill aggregators, right, is effectively that you have lots of different equivalent sets, right, that your physical analysis might need to touch, right? So like if you're analyzing a particular logical region, the metadata for that logical region, about what instances are valid and stuff and what memories, right, might be spread across several different equivalent sets, right? And so you may need to go to each of these equivalent sets, do a little bit of analysis there to figure out which copies need to be issued. But we don't just want to immediately issue those copies to Realm. They might be kind of tiny, right? Like you might want to bulk them up into bigger copies, right? And so that's the purpose of these copy fill aggregators, is to sort of like gather up all of the copy information, that you might need to do, or copies or fills, right, as part of your analysis. And then only once you've traversed all of your equivalent sets do you actually then tell the copy fill aggregator to go do its thing and try to aggregate those copies into as big a copies or fills as possible. And then you can actually do the analysis and issue those things down to Realm. So today we're going to look at this copy fill aggregator object in more detail. Okay, so let's take a look at some code here. Let's start with here we go. This is the CopyFill aggregator class, right? And to refresh everyone's memory, the methods that we were looking at before were these record update methods. And you'll remember that there are several different flavors of these things, right? So you could record a single update. You might record updates that you might need to perform to several different instances. There's the record partial updates, which handles the very nasty case of having partial expressions right here, like this expression on the updates that you need to perform. And then you can also record fills and reductions and stuff like that, right? And so we see some of these methods before. Let's just refresh our memory about what they do, so we can then look at how the CopyFill aggregator actually works. Right, so if we look at CopyFill aggregator, if I can type, record update, right? So effectively what this is doing is it's saying we need to issue a copy from this source logical view to this destination logical view, for the fields in this field mask, for the points in this index space expression, right? And potentially with like a reduction op and stuff like that. Now I'm going to ignore all the tracing stuff because that's all not relevant to just the functionality of this thing, of this class here. The copy across helper method or object, handles when you're dealing with copies across. But otherwise not, mostly what you need to care about are these dest view, source view, the source mask, the expression, and potentially the reduction operator that needs to be performed on this copy. Right, and so, effectively there's some checking here to handle stuff with collective views and stuff, but eventually we call this base helper method here, this record instance update. If we go take a look at that, it's actually right here immediately below us. It actually does something incredibly simple, right? Which is effectively it makes one of these copy update objects inside of this CopyFill aggregator, right? And it stores it in this data structure, this updates data structure that needs to be, that's storing the names of all the copies that we're going to need to perform. And if we go look at the CopyFill aggregator class, well, first off, let's show you up here at the top, there's sort of like a base, we're inside of the CopyFill aggregator class here, right? And so there's a couple of base subclasses types in here that we effectively use to represent these copies, right? So we have a base update class, which sort of is an abstract. It's not abstract. I guess it is abstract. There's a pure virtual method here. But it represents all the updates that need to be performed, and there's two variants of that. There's the copy update and the fill update, right? So effectively storing these objects will represent, copies or fills that we have to perform to update this particular target instance that we're going to be copying to, right? And so, not surprisingly, like a copy update, has an actual instance as a source, right, and a potentially a reduction operation that we need to perform as part of that copy, right? And then a fill operation has a fill view as a source, right? So it's not terribly surprising. So this is when you're just going to be issuing a fill directly to the instance instead of copying from some other instance, right? And so these both inherit from that update class, right? So you kind of have a generic base class, and what that allows us to do is down here in this in this sources data structure, you can actually keep track of effectively, for any given target instance, what are the set of updates that need to be performed to update this particular target instance that we're going to be copying to, right? And so, and you notice there's a field mask set, so it's actually tracking like which fields each of those updates are associated with as well, right? So if you've got a lot of parallel fields that you're analyzing at the same time, right, you might have updates for different subsets of those fields, right? And we've looked at this field mask set class before, so I'll refer you back to that lecture for describing that. Right, and just to tie that back in here, right, this is the updates class. Actually, I should say, let's see, I'm going to make sure I'm pointing you at the right thing here. So this is actually storing this in the updates member variable here, which is actually, so updates is, indexing into the sources data structure here, right? So that sources data structure here, this member variable here that I was showing here is what shows up over here, and we're getting, effectively these updates. There's a reference to the field mask set for this particular destination view that we're copying to, right? And so effectively, we end up saving our copy update that we've made here into this updates data structure, right? And then there's some stuff here for tracing at the end, but again, we'll cover tracing in a future section. Some other things that we do here, just for bookkeeping, we record these views, which help us keep references to them to keep them alive as long as our CopyFillAggreator is alive. Just to keep them alive. We also keep a summary of like all the fields that we're updating, and so we're merging the bit masks here for the source mask into our update fields to record that we're updating those fields and so forth. But the main part here is this updates data structure, and for a particular mask. There's some details here for copy across stuff, which I'm not going to get into. That's what this helper test here is for. But I'll say this is the most common case right here where you don't have to do anything. There's no helper. Yeah, so we're saving that in there. There, as we looked at before, there are other variations of these record update methods. So if we look at the pluralized version of this one, right, where you might have multiple source views and you have to pick, which source views to use to update the destination, right? Like there's some, I think we looked at this method in a prior lecture. But you'll notice that there's some tests here to figure out the ordering in which we're going to issue these updates. But ultimately, they come back to that record instance update method that we were just looking at to actually record, that we're actually doing a copy update. And just to show you the other path for fills, there's also this method here, record fill, which effectively does exactly the same thing, except now our update is a fill update. And so here we're filling the destination instance instead of actually issuing a copy to it, right? But it updates this sources data structure just the same as it did, for a copy update. And so this sources data structure is effectively aggregating all of the updates that we have to do for this particular destination target that we have to copy to, right? There is one exception I should point out here, is that all of these copies and fills that we've done here so far have been effectively normal copies and fills. There's a separate path for reductions, and the reason for that is that reductions have to be applied on top of these CopyFillAggreators. So the order in which copies and fills are done is actually somewhat important, right? And what's going to end up happening, I'll show you a little picture here, is that effectively this CopyFillAggreator is recording all the copies and fills that need to be performed, but they need to be performed in a certain order. And in particular, you have to apply, effectively all of your normal copies and fills first, and then you apply your reduction copies on top of those normal copies and fills, because some of these might depend on like normal copies and fills to initialize the data in, say, a destination instance, and then we apply the reductions on top. And we might need to apply several stages of reductions, right? We might need to apply for one reduction op followed by another reduction op on top of that, right? And the order in which these are done is dependent upon the program order in which people issued reductions in terms of their original application program, right? When they issued the task to Legion, right? So we might need to apply multiple stages of reduction copies on top. And so the copy-fill aggregator is actually tracking this information to remember that, like, if it's a normal copy or fill, it's going in that sources data structure. And then over here, let's tie this back to the code here. There's a separate data structure here for reductions, right? And you'll notice that this is a vector of maps, right? So effectively, what's happening here is you've got a vector. Each of these each entry in this vector is corresponding to one of these stages, right, for reductions. So a particular reduction operator will correspond to one of these stages, right? And then inside of those stages, we record all the destination instances we have to copy to, along with the reduction copies that have to be applied, and those are field masks because we might be applying for multiple fields and so forth, right? So that's the reason that this reductions data structure here is effectively handling multiple different reduction operators for cases that happen. I will say it's very rare to actually get multiple reduction operators in here, but we do have some tests that actually test this and do rely on it. So we do have to have this vector, but I'll say the common case is when you do have reductions, the size of the vector is almost always 1. But there are a couple cases where you've got multiple reduction operators that need to be applied in the same copy-fill reduction operator. And so when you look at these two data structures, the sources and the reductions, just keep in your mind this picture over here, right? You've got stage 0, which are your normal copies and fills. That's corresponding to these sources here. And then you've got, these series of reduction stages that have to be applied. And that's represented by this vector of reductions over here that you're going to need to issue copies from, right? So, and, just to tie that back over here, when we record reductions, you'll notice that we actually have to figure out which entry in that vector of reduction epochs we're going to actually need to update. Well, actually, I should say the reduction epochs actually tell you the reduction operator ID. Let's see. Yeah, so here you go. Right, so effectively this reduction epochs is actually saying, for any given instance, any given target instance, and its destination field IDX, like which one you're doing the reduction to. This is the vector of reduction operators, and it'll effectively tell you for each entry in here, right? It'll say like the corresponding, you search through this vector for your reduction operator ID, and whichever index you find is the same index that you can use to index into this vector up here. And so if you actually look at this code, like one of the first things you do is you actually try to find which index into this reductions data structure here. Which entry in that vector you can actually put your new reduction copy you're gonna issue into, right? And so it's effectively searching through it to see, can we find a prior stage for this reduction operator, and if so, which one can we use? And once we find it, then we can actually make our update and actually record it in the right reduction epoch. And if not, we end up creating a new one, right? So you can actually see the scan here. You're effectively looking through it to try to find the right reduction operator. Right, and then if you don't find it at the end, then you just stick it in a new index in that vector. And so that's an important case for reductions. So we have a separate path for recording reduction copies in here in this copy-fill aggregator. Okay, and if you're curious of who calls these methods, again, I'll refer you back to the equivalent set methods or equivalent set lectures that we looked at before to actually see how we actually call these methods to do the analysis to actually figure out how to issue these copies and fills and stuff like that. Okay, so once we've got effectively coming back up here to the copy-fill aggregator, there's sort of like the two parts of this class, right? The first one is recording all the updates, right? So coming back to our picture here, right? We walk over, our physical analysis walks over all of its equivalent sets that it needs to analyze. And then it records all of its updates, all the copies and fills that it needs to perform in this copy-fill aggregator. And once it's done, then it can actually tell the copy-fill aggregator that it's actually safe to perform its analysis and actually issue all of the copies. And so I'm not going to show you that part today, but effectively what happens is you end up calling this issue updates method. The physical analysis will call this issue updates method. And what that's going to do is actually effectively that tells the copy fill aggregator, hey, I've finished my analysis, like I've done walking over all my equivalent sets. It's now safe for you to go and issue your copies to Realm and bulk them up into as big a copies, grouping together as many fields and points and index spaces as you can to make the copies as big as you possibly can do, right? And so effectively your physical analysis will end up calling this issue updates method, right? And it might give you, again, we'll ignore tracing stuff, might give you an event precondition that you need to abide by. And then there's some extra, a whole bunch of extra cases down here that handle special cases for restrictions and other unusual events and stuff like that. And then it gives back an event saying, this is when all of the copies have been issued, and that's the event that represents, all the copies being done run that this CopyFill aggregator, needed to perform, right? And so let's actually go take a look at this this issue updates method. Let's see here. Okay, so here's our issue update method. I'm going to come back and talk about this guard precondition today. So we're going to skip this block of code for the moment. We'll skip this block of code right here, talking about this guard precondition. We will describe the case for why there might be a guard precondition on this CopyFill aggregator later. Okay, but effectively our next step is to actually go and issue the copies and fills and stuff like that. And you notice, by the way, that this CopyFill aggregator takes a stage argument. And that stage is actually corresponding to this this picture over here that I showed you. In fact, if I actually want to make this slide correct, what I should really have done is do this. The stages actually are numbered like this, and that way you can use these stages as effectively indexes into that reduction vector, right? And -1 is just a special case that knows it means it applies to the normal copies and fills and stuff like that. And so effectively, this is a reentrant method. And what I mean by that is like this method could actually it may in some cases need to preempt itself and then launch a continuation to call itself again later when it's safe to resume running. And let's see, I will, in order to understand why that might happen, I'll try to give a flavor of why that's happening, but we will probably need the next lecture to really understand why you might need to effectively create a continuation to call back into this method with and continue at a different stage than, say, stage -1, right? So we start in stage -1, which means the first time through, right? And you see here, like, if you're in stage -1, right, then you're effectively gonna run the normal copies and fills, and you're gonna pass in, you're gonna call this perform updates method, and you're gonna pass in the sources because that's the stage 0 set of updates that you need to perform is that normal copies and fills. It'll return this Boolean, which will say whether it's safe to pipeline ourselves, and that's where we might need to continue or to make a continuation. Effectively, there are two cases here. There's one case where it's safe to pipeline, and we can ignore these recorded events, and we'll be able to just continue running the next perform updates right away for the next stage without needing to build a continuation. And then there's another case where you actually do need to effectively build a continuation. If there are any recorded events, you're actually going to need to build a continuation, right? And you can actually see that down here in this. So if this is stage -1 right here, right, and we'll skip it on a reentrant call, right, because the stage will actually be greater than -1 by the time we come in the next time, right? And then for each of the reductions, we run their stages as well, right? So effectively here you can see we start at whatever stage we're on, right, and we iterate over all of the reductions that we recorded in this reduction vector. I'm just trying to tie everything back for you. This is our vector of all the reduction epochs that we have to perform, right? And so effectively we're iterating over that, starting at whatever stage we're currently on, right? And effectively we have this pipeline variable that says, is it safe to run these perform updates calls back to back? And we'll talk probably in the next lecture about why that might be the case that you might not be able to do that. But for today, just know that you have to handle this case. And effectively, if you've done one perform updates and you come back around to the next stage, right, and you've got some recorded events that haven't triggered, you may need to effectively build a precondition and then launch a continuation meta task here, which will actually turn around and invoke this method again, but with a new stage, right? Effectively, the next stage past where we are right now. And so, just something to keep in mind is that can happen. And the nice thing about this is like we can easily make a summary event. The summary event is actually, I'll show you where we store this over here on the member class. Here's our summary event. So we can effectively give back an event immediately corresponding to when all the copies are done, even though we haven't finished issuing them yet. So effectively, the first time you build a continuation, you may end up making one of these summary events, and if so, you'll end up returning that right away to the user, who can then go on and do other stuff, even though we haven't finished issuing all of our copy updates right away. Okay, so that's the continuation stuff. But mainly what's happening here is we're calling this perform updates, and we're passing in either whatever stage of the reductions we're passing in, or our sources here in the stage -1 case. And by the time we effectively we go through all these, once we've done issuing all of those things, right, then there's some stuff at the end to record events and stuff that have happened as part of running this copy fill aggregator, and ultimately we return our summary event here that represents all the copies being done. So let's actually go look at this, and some of these, I think we're going to come back today to some of these other, like these guard post conditions and stuff like that. We're going to talk about those a little bit later today. I want to avoid introducing the case that causes that right away, but we will get there today. Okay, so if we look at perform updates, let's actually look in the header file here for it first. Here's the perform updates method right here. So what you notice is that effectively this is taking in one of those stages, right? Effectively a map of all the destination instances that have to be copied to, and along with all the updates that have to be performed to each of those destination instances, right? We might have a precondition that corresponds to something that all of our copies have to depend on. We're going to keep track of all of the runtime events that have to be that are outstanding for this particular stage of the pipeline. If this is an index into the reduction op vector, we want to know that. Some of the other special arguments here that got passed in to issue copies. To issue updates. So these are details. We'll probably skip most of them today, but up here is really the important stuff. Okay, so we can look at perform updates. Okay, and what this is going to do is actually not terribly surprising. So the main thing we're going to do is we're going to iterate over all of our updates, right? So all the things in a stage, we're going to iterate over all the destination instances, and issue the copies and fills and stuff that need to be performed for them, right? So effectively we're iterating over this. I'm going to skip this manage destination events. This is a case where effectively someone has already done the analysis to figure out what all the preconditions are on the destination views. That's a special case that occurs in some cases, so we can do a little bit less analysis, but that's just an optimization. Mainly we're going to need to do that kind of analysis ourselves. Okay, so here's where we actually get into some interesting optimizations that the copy-fill aggregator actually performs. Okay, so the first thing we're going to do is we're going to try and group our source instances together by fields, right? Or I should say our updates, because effectively we're going to look at this field mask set of updates we need to perform and say, what are all the ones that have common sets of fields, right? So that we can try and group them together for those fields, right? So effectively we do a group by on our field groups, or on those updates first to effectively get sets of fields that are ending up in the same that are going to, sets of updates which are going to have the same fields, right? So that's effectively a group by operation, right? And again, I'll refer you to a previous lecture that shows you where this compute field sets API call is done and does this group by operation on pretty much a field mask set with any base type, right? And so you can go look at that group by operation yourself. But once we've got that, now we've got a list of all the updates that have to that share the same set of fields, right? What we can do then is effectively we can get the corresponding mask for all those fields, right? And then we're going to effectively sort all those updates into the copy updates and the fill updates, right? So effectively this is where there's this base virtual method called sort updates on these updates, so you can actually sort them into copies and fills. And if you remember up here, these two we had, effectively a base class, which is this base update class method, and it had this sort method or sort updates method, right, which is a pure virtual method, right? And it's implemented separately for copies and fills. And what happens is, like, effectively, if it's a fill, it'll stick itself in this, or I should say, if it's a copy, it'll stick itself, in the right entry for each of these source instances, stick itself in the copy update vector here, right? Similarly for fills, like, they implement this by just sticking themselves in this fill update data structure here. Okay, so that sorts ourselves into copies and fills. So we've got, effectively a vector of, for this destination view, we have a map of, for all the source views, all their copy updates, right? And similarly, we've got, a vector fills that we need to perform. I'll say in the common case, either one of these will be empty. Either fills will be empty or copies will be empty. You can get cases that are mixed. It might happen that you have to fill like part of the destination instance with one set of points and copy to another set of the instance with another set of points. That can definitely happen, and this code reflects that and can handle that case. But the common case is probably that you'll either have fills or copies, probably not both. This does the right thing in either case, but effectively expect when you come through here that you're going to end up just with either fills or copies, but probably not both. Right. So we sort of,
would this happen? Would this happen when you've like instantiated half of a region in another place,
Yep.
and then you've like zero filled the other half?
Yep. Exactly.
And now let's say you're instantiating the full thing, so
exactly
half needs to be copied, right?
That's exactly the picture you should have in your head. Yes. Yep.
Okay.
And to your CopyFill aggregator might have recorded that you have copies and fills, right, for the destination instance, right? But they've got different expressions, right, that are non-overlapping with each other, right? And so when we go to sort those things here, it'll tease them apart into the copies and the fills, right? Yep. Okay, and once we're done with that, this actually gets pretty straightforward. So we're going to call this, if we've got fills, we're going to call the issue fills method. And if we got copies, we're going to call the issue copies method, right? And you'll notice, like, after that, there's a little bit of extra stuff here for checking for this pipeline condition, which again we'll probably talk about at a later date. But other than that, nothing else happens. We go back around the loop and we do the same thing for the next destination instance, right? So like this part is all very straightforward. Let's look at issues fills first, and then we'll look at issue copies. Okay, so here's issue fills. Again, this is where we've got our vector, we've got our target instance we're trying to issue to. We've got our vector of fills that we need to perform. It's probably the common case there's only one fill in here, but it'll handle the case where we've got multiple ones. Right, and we've got our set of recorded events that we're going to return back. Here's our event precondition and our fill mask and some tracing stuff and other things that are special cases. And there's really only two cases in here. It's pretty straightforward. So we have a special case for fill size equals 1. Effectively, the case where you've only got a single fill is a special case. So we can pull out our fill update. And then what we can do is we can turn around and tell our destination instance, please issue a fill from this fill view with this event precondition. Here's your predicate guard, your fill expression, the operation you're performing the analysis for, the region requirement is for. We'll skip this match space stuff here, but here's your fill mask, tracing stuff, and other things. But effectively, this will go issue that fill from this fill view to this target view, right, and give you back an event corresponding to when that fill is actually performed, and that's pretty straightforward. And notice, if effectively if we have a result, then we might record it if we've been asked to track the completion events for these fills as part of this CopyFill aggregator. Same thing with these destination events. We could save it there if it exists. So it's all pretty straightforward. In the case where we have more than one fill, where we might need to fuse them together, right? Potentially we have multiple fills, and we want to see can we join those two fills together, right? And so in order to do this safely, right, effectively what you have to do is we have to join together fills. Actually there's an extra condition here. You can't just merge them if they have the same fill view, right? You actually have to have the same fill view and predicate event, and we'll save why you need that predicate event for another day. But effectively what we're checking for is, like, if you've got the same fill view in the fill updates, right, then it's safe to merge together the two fills from different fill expressions, right? You can actually take two index-based expressions and mash them together, right? In that particular case, because you know the value you're going to be filling for is the same value, right? And so effectively what we do is we look over all these fill updates and we sort them based on this key, right? We effectively create this key, which is the fill view as well as the predicate guard, and we stick it in there, and then all the ones that are going to end up in the same set here, right, are effectively things that we're going to be are going to be index-based expressions that we can actually merge together, right? So we build up this data structure, and then once we've got it, then we can iterate over this data structure and merge together the index-based expressions for fills that are that share the same fill view and predicate event. Right, and by merging them together, that effectively creates an aggregated fill, right, that represents the union of all the index-based expressions for those updates, right, and then we can just issue that like a normal fill operation, filling the target instance from our fill view, right, and passing in all the other stuff that needs to happen, right. And so this is actually where you get to your aggregation, right, this merging together of index-based expressions. Shows you that you can actually group together fills that maybe initially look disjoint from different equivalent sets, but now we can actually merge them together. Okay, hopefully that makes some sense, because now we're going to do the copy version of that. Okay. So issue copies is the corresponding method for doing the same aggregation except for copies. It works pretty similar, modulo some special cases. I'm going to skip this first case because it has to do with collective views, and we haven't talked about collective views yet. But
can I ask a question about the fill?
Go ahead. I'll go back.
The union.
Yep.
Where you do the union? Does that also coalesce? Like if it's contiguous pieces, does that become one index space?
It becomes one index space. And Realm's representation of the sparsity map for that index space will union together rectangles where possible. So so this is Legion's union, which effectively, there's actually a common sub-expression elimination engine in here, right, which will check to see if we've ever done this union before, and if so, we'll return the result. If not, we'll actually tell Realm to go compute the union of like the two index-based expressions, right? And that might be easy. It might be like two rectangles, and maybe one of them dominates the other one, and then the union is is the same as one of them. That'll get detected, right? But effectively, if they're two separate rectangles, or if they're each groups of rectangles, right, then Realm will try to actually compute a new sparsity map for those things, and where possible, Realm will union to actually join together rectangles into a more concise representation of the sparsity map for those things. Does it make sense?
Yeah. Essentially, fall back to Realm to
actually compute
in the base case to compute then try and combine rectangles if possible.
Exactly. So Legion actually doesn't do that computational geometry. Realm is what handles all that. Legion just has names for all those things, but we do try to avoid calling Realm where we can detect the case where we have already done the union, for those two sparsity maps before. Right, so that way we don't compute it over and over again, because that would be expensive, right? So yeah, so if you're doing a repetitive computation, maybe you do the same aggregation over and over again at every stage of your program, right? Then you won't actually recompute every time, right? It'll only be the first time through that you'll compute that new sparsity map.
Yep, makes sense.
Okay, great. Okay, so issue copies is actually very similar to issue fills, except now we've got, effectively we've got a target instance that we're trying to fill in, and then we've got, this map of, source instances to update this target with, as well as the sets of vectors, corresponding to each of those source instances. And I'm going to skip the collective copy case here because that's a special case and we haven't talked about collective views yet. So this is, and actually, for those that are interested, this is actually inspired by Q-numeric. So, you can come back and read this this comment a little later and take a look at that. That's handling this views gather copies case. But the main blob of code is down here in this loop right here. Right, so we're going to iterate over our destination views that we're going to need to issue copies for, and we're going to need to look at all the copies that need to be updated to this. Actually, I should say we're iterating over the source views, right? So these are the source views here that need to update that target destination view. and we're going to see how many copies we've got to issue from the source view. It's important to notice that like we're only going to be fusing together copies that have the same source and destination pairs. We don't try to sort like we could conceivably try to fuse together realm copies that actually had like different sources, right? And say like, hey, we can actually fuse together the expressions for those things. But realm is actually going to turn around and split those off later anyway. So effectively, we don't try to do any fusion across like different source instances for any given destination instance. So effectively, we're going to look at for the source one and see if there's any, copies that we can fuse together just for the source destination pair that we're going to be targeting. Right. There's the common case where there's only one, right? And we don't have to do any analysis, right? At this point, we can just get the source view, we can get our copy expression, and then we turn around and issue the copy, update this target instance from the source instance. Here's our precondition, our predicate guard, our reduction operator, copy expression, our operator, our which region requirement we're on, our mask of fields, all the kinds of things that you pass into this copy operation. But this will actually issue the copy, and I promise you at some point we'll actually go look at this copy from method, and then we get back our event saying when that copy is done, which is pretty straightforward. And again, we can record that if necessary. In the case we've got more than one update copy, well then we're going to need to try to group them the same way that we tried to group the fills before. Our key here is a little bit different than the one before. We don't have to worry about the predicate stuff in this particular case because we're guaranteed to have the same predicate in this case. So here our keys are just the instance view and the physical manager for the destination view, right? So you can see, or actually I should say the source view. So you can see our key here. Effectively we iterate over all the copies. We get the source, the views, right? We stick them in there, and then we save them in this fused expression saying, what are all the ones that share the same, effectively the same source instance view for each of these copies, right? Let's see. Okay. Yeah, you can see a little bit of why that's happening because of collective instances and stuff. That's why you have to have two things here instead of just one. But it's both the view and the physical manager. So, just something to keep in mind. But we haven't talked about collective instances yet, so we'll have to come back to that at a future date. But once we've got effectively all the source instances that can all be fused together, right? Then we can turn around and do the same kind of fusion operation on all those index-based expressions, right? To get a fused expression for doing that copy, right? And then we can go ahead and issue the copy to the target, get our event, and away we go. Okay, so that's all pretty simple. And that's effectively how the CopyFillAggreators actually, do that fusion of different copies and stuff to make sure to group them into as big a copy as possible to issue to Realm. And this actually turns out to be a pretty important optimization. It's a lot of work for Legion to do this, but the value to Realm and to the application is quite large because it's much better than issuing lots of little copies and making Realm work really hard to run all those things. It's much better to bulk them up and then run them as one big copy. And you effectively the value out of Legion doing a little extra analysis is worth it, and the reduced overhead that Realm has to perform to perform lots and lots of little copies. Okay. Any questions about this before I talk about some of the more interesting cases of CopyFillAggreators for the rest of the time? Okay, no questions. All right. So let's talk about some of the challenges that can occur with CopyFillAggreators. Okay. So here's a tricky case. So one of the things that might happen, imagine you've got, I've got an extra arrow here. Probably don't need that one. Imagine you've got two read-only physical analyses that are actually coming from different tasks, right? So these two tasks are trying to map, let's say two read-only tasks are trying to map the same region requirement with read-only, or I should say two tasks are trying to map the same region requirement with read-only privileges, right? So they've each created their own physical analysis, and Legion actually allows those two tasks to attempt to map in parallel, right? In fact, they may even be mapping on different nodes, right? Running their physical analysis on different nodes, right? So they may not even be capable of being aware of each other, right? And each of those physical analyses are then going to go talk to the same equivalent sets, right? To try and issue updates to update to update their particular target instances and stuff with valid data, right? So they're each going to go talk to these equivalent sets. They might not even talk to them in the same order. This read-only analysis might talk to this equivalent set first, and then talk to this one potentially on a remote node later. Maybe this one sees, oh, this one's on my local node, so I did that one first, and then I'll do this equivalent set on this remote node later, right? So they may not even traverse the same equivalent sets in the same order, but they'll definitely go visit them all at the same time, right? And there's a problem here with that, right? Because like each of these analyses, right, when they traverse these equivalent sets, they might end up issuing, they might not, and they don't actually issue, but what they do is they record that they need to perform copies, right? But once they've recorded they perform copies, they haven't actually issued the copies to those destination instances yet. So like, let's say like the original valid instance for the data is actually an instance A, right? And so this first analysis over here comes through, and it records that it needs to do a copy to update instance B from instance A in its CopyFillAggregator, right? And then this physical analysis comes along and talks the same equivalent set and records that like, oh, instance B is actually closer to me than instance A, so I'm going to record in my CopyFillAggregator that I need to issue this copy from B to C. Well, that's actually interesting now because we've got these two CopyFillAggregators, right, that actually need to be chained together. They actually have to issue these copies in the right order. If they don't issue those copies in the right order, you can actually miss dependencies in hooking up these copies, right? You're going to need this copy here to depend on this copy up here, right? And so what that means is that these CopyFillAggregators have to issue their copies in the right order, right? And the reason for that is that, when you traverse this equivalent set, you didn't actually, even though it looks like you updated instance B, you actually haven't issued the copy yet to update it yet, right? And so that effectively causes problems, right? You actually have to make sure that these CopyFillAggregators in these read-only cases are actually ordered. It turns out it happens in more than just read-only cases. You can also have this happen in reduction cases as well, but that's a separate discussion. The read-only one is probably much more common, and so what we need some way of making sure that if we've done a copy. If one of these physical analyses has walked through this equivalent set and actually issued a read-only copy, right, to update, the set of valid instances in this equivalent set, it needs to record itself somewhere in this equivalent set to know that it's actually safe, or so that anybody else who comes in and also wants to issue a copy will actually make sure that their CopyFillAggregators depend on the CopyFillAggregators of any prior analyses that actually had come through that equivalent set. And so that actually, will show up over here. Let's actually go look at the equivalent set class here. Okay, so in the equivalent set class, what you will notice, we'll scroll down through all the methods and stuff that exist in this class. There are two interesting data structures here to help us out with this particular case. So you'll notice that we have read-only guards and reduction fill guards. Okay, and the case I'm talking about here are the read-only guards. The reduction fill ones are very similar to the read-only case. Effectively, this is just like when you've got multiple reductions, whichever one gets there first, it may have recorded that it needs to issue a fill to reduction instance to initialize it, right? And so you might have multiple reductions that map in parallel that need to handle that case. But the one I'm describing here is this read-only case where you've got multiple read-only analyses, right, coming through and looking at this equivalent set and potentially recording their CopyFillAggregators, as having performed a copy. You notice this doesn't say CopyFillAggregator. It actually says CopyFillGuard. And that's because CopyFillGuard is the base class for CopyFillAggregator. So you can see CopyFillAggregator class here inherits from this base class CopyFillGuard. And this CopyFillGuard is a much simpler class. And you can actually create a CopyFillGuard as on its own. It doesn't actually issue any copies. All it does is records that there's some outstanding, operation or CopyFillAggregator kind of thing, right, that needs to be performed, and it has an event for when, effectively when all of the effects for that CopyFillGuard have finished, right? So then you can go turn around and run your CopyFillAggregator, right, to depend on it. The reason we have this CopyFillGuard class is that, one thing that might happen, I come back to my pictures over here. one thing that might happen is like, it might be the case that like this physical analysis records, does its copy update, it records its copyfill aggregator as a copyfill guard, right? Effectively because it issued a copy to change the set of valid instances in here. And then maybe because of migration, this equivalent set migrates to another node, right? And so you don't actually want to move the whole copyfill aggregator when that happens. You just want to move like, effectively a shadow of what that copyfill aggregator was and the name of the event that corresponds to when the copyfill aggregator is done running. And so if that migration takes place on that equivalent set, while the copyfill aggregator is still outstanding, then you'll just get a copyfill guard on the remote node. But in general, these copyfill guards actually will be pointers to copyfill aggregators, like on the same node. So that's just something to keep in mind. That's the reason that there's like sort of this base class instead of like needing to reference the actual full copyfill aggregator class. So this is actually the stuff that you might need to know on a remote node. But coming back to these copyfill guards down here, where'd they go? Go back to equivalent set, scroll down. Okay, yeah, these read-only guards here. Right, so effectively what happens is the copyfill aggregator will keep itself as a guard on this equivalent set up until the point where it's actually done issuing its copies. At the point where it's done issuing its copies, it can actually remove itself from being a guard on this equivalent set. Right, and what that means is that any later, so one thing that could happen is like this read-only analysis could, effectively traverse this equivalent set, record some copy updates in its copyfill aggregator, could do its analysis over here, finish this one, and then run its copyfill aggregator, at which point the copyfill aggregator will remove itself from the guards for this equivalent set, right? And then this later analysis comes in and it won't even see that there will be no guards left there because the copyfill aggregator is done running, right? But as long as, the copyfill aggregator is outstanding, hasn't actually issued its copies yet, it will remain as a guard inside this equivalent set. So if this analysis comes through and needs to create its own copyfill aggregator, it will need to depend on that, right? And so one thing that I skipped over this in an earlier lecture, but one thing that you'll see is like when you actually make a copyfill aggregator, and we'll go look at this in just a sec, you'll actually check to see if there are any prior guards in this equivalent set before making a copyfill aggregator, right? And if there are any guards for the fields that you're analyzing, you'll make sure to chain it, to depend on all the on the prior copyfill aggregator for those fields, right? So let's actually go look at that. That little bit of code here. Well, let's see here. If we go look at update set here, let's find one of the places where we make a copyfill aggregator. Let's see. Right, so where's the read-only case? There's the reader-write case. Right, here we go. So like, effectively you can see here, this is the read-only path, right? And, effectively before making our copyfill guards, we have to check to see if before making our copyfill aggregators, for this particular update analysis, right, we need to iterate through these read-only guards, right? And we're going to check to see if any of them overlap with our field mask, right? Effectively the fields that we're analyzing to see if there's any copyfill guards for those. And if there are, then we're going to chain ourselves and effectively make a new copyfill aggregator that's effectively going to be dependent upon the prior copyfill aggregator that occurred, in this equivalent set, right? So that way we can chain up our copyfill aggregators, right? And that's actually one of the reasons that, actually coming back to this picture up here, the same physical analysis might end up having several copyfill aggregators, right? You might think that you could get away with just doing one that traverses all of these equivalent sets, right? And aggregating all the copies across, all of them. But that's only true like if you've got like read-write privileges or something, you're the exclusive one, analyzing those equivalent sets. If you've got a read-only case, you might end up racing with other read-only updates to create copyfill aggregators, in which case you might end up making multiple copyfill aggregators for the same physical analysis because maybe this one doesn't depend on anything, but this one depends on some copyfill aggregator that was actually made by some prior operation. And that can limit your aggregation capabilities, but in practice it doesn't happen terribly often. And it's actually important that you do this and do this chaining properly, otherwise you can get cases where you can actually deadlock the runtime. Like if you actually tried to not chain these copyfill aggregators properly, you could actually create cycles where one read-only analysis, effectively analyzed this equivalent set first, then did this one, and this one did it in the other order, and their copy fill aggregators end up depending on each other. Can get very tangled up very quickly if you're not careful. So effectively, these copy fill guards, or I say these read-only guards here in the code here, right, are effectively making it so we can actually chain these copy fill aggregators correctly, so that they actually do end up issuing their copies in the right order between themselves, right? And so, and actually to tie this into the code, let's actually go look at the copy fill aggregator class. Let's see here. So copy fill aggregator class has effectively two events, the guard precondition and the guard postcondition. Here's the guard precondition, right, which effectively says this is the precondition that this copy fill aggregator is not allowed to start until this runtime event has triggered, right? And this event will actually, if it's a no event, that means that there's no prior copy fill aggregator that this copy fill aggregator depends on, right? But if it's if it's an actual event, right, well then that came from some other, copy fill aggregator's post condition, and actually that exists on the copy fill base class up here. Here's let's see, where is the guard post condition? Yeah, the guard post condition effectively represents that, right? And so that, it could be I've got this non-aggressive aggregators case. This is almost never defined, so like you can pretty much ignore it. So this guard post condition effectively says this is when this copy fill aggregator has finished issuing all of its copies, right? And so that allows for the chaining of those copy fill aggregators, one back to back on top of the other, effectively creating a chain of them to actually issue their copies in the right order. And if you issue those copies in the right order, then what happens are these copies will hook up their dependencies correctly, right? Which is actually necessary for correctness, right? You might need to issue from instance A to instance B. That copy has to be done first before the copy from instance B to instance C can be run, because the data from A needs to be in B before you can copy it from B to C, right? And so that chaining is absolutely essential to getting these copies and their dependencies issued correctly. So effectively, that's what's going on there in order to make this code work correctly. Let's see. I think that's and yeah. I will also just summarize. We saw the read-only guards data structure here. There's a similar case that can happen for reductions. You can go take a look at this one for yourself, but it's literally exactly the same concept, just like with reductions, trying to use the same reduction instance and needing to make sure that all the fills are done to that reduction instance. So just something to keep in mind there. But that's what these guard things are doing. Okay. So with that, I'm almost out of time, so I'm going to stop here and leave it open for questions. And next week will be another Legion week before we go back to doing Realm. Okay.
I think I spaced out a little bit in the end here. Where are those guards stored?
These are in the equivalent sets. So this is in the equivalent set class. So effectively think of it like this. We're inside the equivalent set class here, right? And the read-only guards are a member variable of the equivalent set class, right? And what they're recording is effectively, just to come back to the picture, if you issue a copy, right? Let's say you're analyzing this equivalent set right here, right? This physical analysis comes in, right? And it says, okay, instance A is the current valid instance. I need to issue a copy to my instance I'm trying to map, which is instance B. I'm going to issue a copy and store that in my copy fill aggregator. But then I'm going to save instance B as a valid instance in this equivalent set, right? But technically,
but does this update need to happen atomically across all equivalent sets?
No. That's kind of like the game we're playing. Like effectively, like each of these equivalent sets have a lock that guarantee that these analyses traverse them in some defined order, right? Like effectively, whichever analysis gets to this equivalent set first, we'll do the update. We'll do its analysis first, right, to figure out what copies to update and stuff, right?
So there's an ordering of the equivalent sets that all analyses or all copy fill aggregators must take the locks in. right?
Well, the analyses, yeah. So all these analyses have to serialize their access to the equivalent sets, right? So it's not safe for two analyses to be analyzing the same equivalent set at the same time, right? Like that
Mm-hmm.
that will trip you up. And I think we saw that in a prior lecture. There's an analysis or there's an equivalent set lock that effectively that you get before you run your analysis on that equivalent set, right?
Mm-hmm. Right.
Right.
But in
And
this weird scenario where you were saying, if the left analysis processes the left equivalent set first, and the right one processes the right equivalent set first, then you're going to run into trouble, right? So
well, that's part of it, but actually that's not even the key part. The key part is like let's just focus on this left equivalent set, right? So initially, like the valid instance for this equivalent set is instance A, right? The bad scenario that could occur, right? Especially this analysis comes in, it looks at this equivalent set, and it says, okay, I need to issue copy from instance A to instance B, right, to bring my instance B up to date that I'm trying to map, right? And it performs. It says I've done this copy and I've recorded it in my CopyFillAggreator, but my CopyFillAggreator hasn't actually run yet to perform that copy yet, right? It's sort of like buffered, right, inside of the CopyFillAggreator, right? Now this analysis comes in over here and talks the same equivalent set and says, okay, I need to issue my copy to update instance C, and I'm going to pick instance B as the prior valid instance, right? And my copy that I recorded, my CopyFillAggreator is going to issue the copy from B to C. But again, nobody's actually run these CopyFillAggreators yet, right? Now imagine a scenario where, like, effectively this analysis finishes its analysis first and tells its CopyFillAggreator to run first, and that will issue the copy, to the rest of Legion and Realm to say, run this copy first. This copy will not record a dependence on this copy in that case. Like the CopyFillAggregators have to have issued their copies in the right order in order for these dependencies to get hooked up correctly, right? And if you miss this dependence on this between this copy and this copy, that will cause a race, right? And then you
and you do this through user events that
yes
get triggered at the end of the copies, I assume.
Effectively, I mean, they're not really user events. They're user events over here to help chain these CopyFillAggregators together. For the rest of Legion, as long as you issue these copies in the right order, then the right thing will happen. So if these CopyFillAggregators run in the right order and issue their copies in the right order, and we'll talk about this a little more the next time, then I promise you that the rest of these dependence analysis will hook itself up correctly. But if, for example, this CopyFillAggregator ran first before this one did, and it issued its copy to the rest of Legion Realm before this copy got issued, then you might miss this dependence from this copy to this copy, and then
So if these copies haven't been emitted yet, and there's a task coming later, how can you hook that task up before the copy has even been emitted yet?
Well, that's so I didn't show you this part today, but effectively, actually, we can actually try and find this right now. Even tasks that come through and maybe try to use, let me just describe the scenario. Even tasks that might come through and try to use instance C and record like their task is using instance C here, will actually know that they can't even do that until this, like the prior guards, which in this case would be this CopyFillAggregator, right, had actually finished running before you tried to do that registration. So
that even stops the mapping from happening, right?
It effectively, yeah. So it won't actually stop the mapping per se, but it pipelines it so that effectively. Let me see if I can find this code. So actually, let's see. So this is like in the read write case. Let's assume. Yeah. So effectively, let's see. Where did it go? Yep, here it is. Actually, is this the right one? I'm trying to find the place where we find all the guards.
We can also pick it up next time if
so
people need to go.
Yeah, I'm happy to stick around as long as people need to, but let's see. I'm trying to find the place, but effectively what's going to happen is that this analysis is actually going to record dependencies. I think it's this record guard set. I'm trying to remember. but I can tell you what does happen. I'm trying to remember where the code is for this, but effectively, like even if the analysis doesn't issue any copies, if it's a read-only analysis, it will actually record any guards for copy fill aggregators that were performed before it, to make sure that it doesn't try to actually like record any record itself as a user of like instance C until all the copies have been issued, right? Because as you point out, like even a task trying to record itself, as a user of instance C, it'll need to wait for that copy to have been issued, right? So that this copy could have recorded, itself as a user of this instance before, whatever task comes along and records itself. So pretty much anybody can come through and record itself, or like anything that's read only will have to record any of the read guards, that might be existing in that equivalent set before it can try to do other things.
Good. Yep.
So that's going to be the invariant, and it's actually a very crucial invariant. And then we'll talk, like next week, I hope we'll actually look at the views and talk about why just issuing things in order is the right invariant to maintain. But we'll talk about that more next week.
Yep.
Okay, did I satisfy your curiosity for now?
Yeah, for now.
Yep. Okay, good. All right, any more questions? All right, cool. Next week's Legion week. We'll see everybody then.